Hey, this is Brock Lemires, and in this video I'm going to continue introducing the diode, and specifically I want to talk about the constant voltage drop model for a diode, which we use to analyze circuits that contain diodes. And this introduces a very powerful concept in electrical engineering, which is called abstraction, which is something we use very frequently with nonlinear devices. Okay, so let's remind ourselves how a diode works. This is the symbol for a diode. It's a polarized device, meaning that it matters which terminal is which. And so you have an anode and a cathode, and under normal operation, current flows one way, flows from the anode to the cathode. And this is the IV curve for a diode. And what happens is that as you increase the voltage across the diode, you have to overcome the barrier potential due to the p-n juncture behavior, which we covered last video. And at some point, once you kind of shrink down that depletion region and you get rid of that barrier, then the diode will start conducting current. And once it starts conducting current, it just is a short circuit. It just looks like a wire, and current will hammer through it. So this is the actual IV curve for a diode, and we characterize the point at which that depletion barrier or that barrier potential goes away as the forward voltage. And it's a fixed voltage, which is a specification for a particular diode. So when you look at a diode data sheet, it'll be like, oh, you have a forward voltage of 2 volts. That just means that that's the voltage where the diode essentially turns on and conducts current. So it's actually an exponential ramp though. So if you look at this, it kind of has 0 current or very little current, very low current, and then once it gets above this forward voltage, it increases drastically. And also you notice that once it turns on, the resistance of the diode is 0. It looks like a wire, and so you can't develop any more voltage across it, and so the current just goes way up exponentially, and you can't really develop any more forward voltage across this. And the equation for a diode is this, right? It's I is equal to this IS, which is called the saturation current, and that's a property of the semiconductor material. And then it's got this multiplied by this exponential, where it's like e to the voltage across the diode over N times VT, where N is the diode ideality factor, so it's either perfect or not so perfect. And then VT is the thermal voltage, which is Boltzmann's constant times the temperature in Kelvin over the charge of an electron, and that's usually about 26 millivolts. Okay, so you got this equation, and you're like, oh, well, this is piece of cake, right? I mean, let's do some circuit analysis. We got all the equations that we need, and so let's do not a classic, like an easy example where you're like, all right, here's what I want to do. I got myself a 5-volt supply. Let's say I got a 220 ohm resistor, and then I got a diode right here, and I'm sitting there trying to solve for, right, so we want to solve for the current through this thing based upon, this plus or minus VD. And you're like, actually, no, I want to solve for VD, and I kind of know this current equation, and they're all related, so this is going to be really easy to do. So let's go ahead and write, KVL around this loop. So I'll do KVL, and what I'll do is I'll say my rise is equal to my drop, so I got 5 volts as a rise. That's equal to plus or minus V1. So I got V1 plus VD. And then what's amazing about this is that V1 is simply I multiplied by 220 plus VD. And then I have a constant right there. And now I can drop in my awesome equation for a diode. So I'm like 5 volts is equal to IS, which is a constant I get. And then I have E to the VD, which is a variable, and then that's over N, which is a constant, and then VT, which is a constant, minus 1 plus VD. And so I can actually solve now. I have an equation which is in terms of VD and numbers, and so I've got it. Okay, right? Wrong. This is called a transcendental equation, which is an exponential. And what transcendental equation means is that it transcends algebra. That means you cannot isolate variables using algebraic rules and manipulations. So we have an equation right here it's absolutely valid, but you cannot bring down this VD term out of this exponential. So you are essentially stuck. That's as far as we can go. The only way you could solve this is to put it in a computer and basically do a numerical solution where you just guess and check check and hopefully you get to the right answer. So we immediately have been confronted with an equation that is true about the behavior of this diode, and it full-blown sucks. It is completely useless in reality. When you go to build diode circuits, you can't use that. So what we need to do is this thing called abstraction. Now, what is abstraction? Abstraction is the term we use for when you have some device or some system and it has a behavior that is complicated, and it's more complicated than we care about. So what we do is we build a simplified model for it, and we come up with some description for how the system works, and we give up accuracy. Okay, we know that we give up accuracy, but if we can use the abstract model or the simplified model, we can get pretty dang close to the result, and then we can come back later and basically build it and test it. So now let's look at this model. We have a very simple model that we can use for a diode, which is called the constant voltage drop model, or CVD. And what we do with this model is we simply say the diode is either on or off. And if it is off, there's no current that flows through it, and you can model the diode as simply an open circuit. Okay, and so if you looked at the circuit and you figured out that the diode was off, and you know it's off when the voltage across the diode is less than the forward voltage. Okay, so if the specification for the diode is your forward voltage is 2 volts, and you look at the circuit and you say, well, there's only 1 volt across it, the diode's off. That means that you can replace the diode symbol with an open, and you know that there's no current that's flowing through it. It can certainly develop a voltage. It does have a voltage on it, 1 volt in this example, but it's not on. So that means there's no current, and then that allows you to solve for a whole bunch of other stuff in the circuit. Like, for example, if there's no current through a resistor, there's no voltage across it. Then you have the case where it's on. And now when it's on, it can conduct current. Okay, and it can conduct as much current as you want because you replace the diode symbol with a DC voltage source that has a value or a voltage of the forward voltage. So you essentially say, as soon as it turns on, then the diode will maintain a voltage equal to the forward voltage. And if you replace it with a DC voltage source, there's no resistance through that. So you could essentially have infinite current that flows through it until you blow it up. Now, you know immediately that you can't put as infinite current through it. So you always have a diode in some circuit that has a resistor that ends up limiting its circuit or limiting its current. So now take a look at this. This is a model. The blue line is our new constant voltage drop model. The red is the real behavior. Now you notice they're not exactly the same, and that means that there's error in this model. So we know that before the voltage across the diode reaches its forward voltage, there is current that flows. Okay, there is a little bit of current that flows, but our model won't allow that to happen, and that's fine because we're close enough. And we know that after it turns on, it does develop a little bit more voltage as the current goes up, but it's like, you know what? Who cares? Our model is simple, and it will allow us to actually solve circuits quickly, build circuits quickly, and then we can go back later, and if we want to know the exact current, we can just measure it. Okay, so let's put this to use. Let's do a couple examples of this constant voltage drop model and see how it's used. Okay, now we're going to rely on some of our prior circuit analysis techniques here and some intuition. Okay, which hopefully we have. Okay, so let's take a look at this circuit right here. So I'm going to come along, and you are going to basically look at this thing, and you're going to do this, this, and this. And what you're faced with is the following. You always approach a diode circuit and you say, hey, is it on or is it off? And if it's on, you draw a different circuit, and if it's off, you draw a different circuit. In this situation, we are actually given the voltage, okay? So we are given the voltage source, and it's 0.5 volts, and then we're also given some other things in the circuit. So for example, we're given that this is a 220 ohm resistor, and we are given the forward voltage of the diode, which is in this case, it's 0.7 volts. This is a specification of the diode. Okay, it's a specification of the diode. So we come along here, and I want to know a couple things. I'd like to know the voltage across the diode. I'd like to know what V1 is, and I'd like to know what I is. Okay, so that's what we're trying to solve for right here. All right, so it's like, okay, first question, is it on? Now, here's the whole thing about it. You look at this and you say, I have to have a voltage across the diode that is equal or greater than 0.7, which is the forward voltage of that. That's when it turns on. I look at this circuit and I start analyzing it, and I realize immediately that my voltage source is only 0.5, and it's the only voltage source in the circuit. That means there is not enough voltage coming from the source to develop more than 0.7 in the circuit. So the answer is no, it's off. Okay? Once I know that, then I can redraw the circuit, okay, using the constant voltage drop model, which looks like this. I'm now going to redraw this. I still have a voltage supply here that's 0.5 volts, and I still have a resistor that is 220 ohms, and now I have an open circuit, meaning that the current is equal to 0. Okay, so I have I is equal to 0 because there's no circuit here, right? It's an open circuit, meaning that there's no closed path. Now, that is one of my first solutions, right? So I have I is equal to 0. So now let's go and try to solve for some of the other things we care about. How about V1? Well, let's see, plus or minus V1. What is the voltage across a resistor? Well, voltage across a resistor is governed by Ohm's law. So it's going to be I multiplied by R. But guess what? We already know that since the diode is an open circuit, this is equal to 0. That means V1 is equal to 0. So if there's no current through a resistor, then V1, there cannot be a voltage across it. So I have now solved for the other two. So I've got I is equal to 0 and V1 is equal to 0. Now the interesting thing, and this is something that's kind of strange, I guess, when you first start analyzing diodes. What is the voltage right here, plus or minus VD? Just because there's no current flowing through the diode or this open circuit doesn't mean that you can't have a voltage develop across it. Just think about like a battery, right? A battery has 9 volts coming out of it, and it doesn't have to have, it has 9 volts even if current is not flowing. So you can absolutely have a voltage across 2 points without current flowing. So now if I came along and I applied a circuit analysis technique like KVL, I could come along and I could say my voltage rises equal my voltage drops. So let's do KVL. And what I'm going to do is I'm going to come along here and I'm going to have a voltage rise across the source. So I'll put my rises on the left, and then I'm going to drop across V1, and then I'm going to drop across VD. So I come through here, and that's my equation. Well, lo and behold, I have already solved for V1, that's equal to 0 volts. And so I can actually come in here and immediately write that the voltage across the diode is 0.5 volts. And so now I have solved for the 3 variables that I care about. And this is what's weird about it, is that you have a voltage across the diode, but it's just not enough to turn it on, okay? So we have now solved a simple circuit using a diode. All right, let's do another one. So here's another example. In this situation, we have a voltage source of 9 volts. And so now we get to come along and say, all right, now let's do this. So I'm going to plus or minus, and I got myself 9 volts, I got myself a 220 ohmer, and I got myself a diode, okay? And the first question then becomes, same specification as before, okay? So this thing has a forward voltage of 0.7 volts. Question is it on? Okay, so step 1, is it on? And the answer is, you have 9 volts coming from the source that is going to have some voltage across the resistor, which is V1, and then you'll have some voltage across the diode. You absolutely have enough voltage here to turn on the diode, okay? So the answer is yes. Now this circuit's really simple because you essentially know that all the voltage, as you went from 0 up to 9 volts, all the voltage will develop across the diode until it turns on, and then current will start flowing, and once the current starts flowing, then voltage will develop across the resistor. So the answer here is that it's on. It is on. And why was that so important? It's because now I can redraw this using my new model. So here I go. I'm going to redraw this, and I have plus or minus 9 volts as my source, and and then I have my 220 ohmer, and now what I have is a voltage source that is replacing the diode, and it has a source of 0.7 volts. It's like, wow, that is just weird looking, but I guess it's true, right? So here is my circuit. I've got plus or minus V1 right here. I've got a current flowing in a loop, and I've got this thing right here that has no resistance, but it is a voltage. And so now let's take a look at how we could solve for this. I want to find VD, I want to find V1, and I want to find I. So first of all, this is VD, so that's done. Let's do V1. So let's do KVL at around this loop. Okay, and so remember, I'm going to sum my rises on the left and my falls on the right. So I come around, I'm going to rise from negative to positive on the 9 volt. So I go around clockwise. So I've got a 9 volt as a rise. And now let's do my drops. I drop positive to negative across V1. Okay, and then I have positive to negative over the 0.7. So I go 0.7. And now look at this. I actually have isolated V1. All I got to do is subtract 0.7 from both sides. It turns out that V1 is equal to 8.3 volts. Holy cow, that's pretty dang awesome. So as soon as it turned on, it clamped at 0.7, and all the rest of the voltage was then across the resistor. Well, now the last thing to do is this. How do I solve for I? Well, I in diode circuits is always limited or dictated by the resistance. So once we know V1, I can write Ohm's law. V1 is equal to I, which is the only current in the loop, multiplied by resistance. So I can come along and I can say V1 is 8.3 volts is equal to I multiplied by 220. Now let's bring out a buddy here. I come along and I say, okay, I'm going to divide both sides by 220. So I got 8.3 divided by 220. And here's what I get. I is equal to 37.7 milliamps. And I have now solved the circuit again, this time when it's on. It's like, all right, this is okay. Okay, that's pretty sweet. Let's do one last one. Okay, let's do one last one where this is a very common circuit too, or a common question that people ask is, if you have, let's say you have a circuit, plus or minus, and you're going to do this, and you're going to have a diode, and this is still our 220, this is VS, and my diode has a forward voltage of 0.7. And the question is this now, instead of being given the voltage source, I want to know what the voltage source is the moment that this diode turns on. Okay, now this is an interesting one because it's the transition between being off and being on. Okay, so now when you think about this, here's what it means to be right in between on and off. Okay, so I'm sitting right in between on and off. So as I transition, the voltage across the diode is equal to the forward voltage. That means it's on. Okay, so it is turned on. However, it's just turning on. That means that at that little instant, I through it is equal to 0. So that's how you solve the moment, the instant that this thing turns on. And you can almost think of like VS as you're ramping it from, 0 up to something. Now, at those two characteristics, I through the diode is equal to 0 and the voltage across the diode is 0.7 to turn it on, allow me to solve for the rest of the circuit. First and foremost, okay, I can immediately solve for V1 because if I know that there's no current in this loop, I can use Ohm's law and say V1 is equal to I multiplied by 220, and I know that if I is equal to 0, then V1 is equal to 0. So V1 is equal to 0. And I can say, okay, that's cool. But then the reason I did that was because I want to write KVL around this loop. So I'm going to do KVL around this loop. And I'm going to come around, I'm going to say my rise on the left is VS because I went from minus to plus. Coming around clockwise, I went plus to minus. So that's equal to a drop. And then plus to minus, that's equal to a drop. But I already know the number. So it's 0.7. And so now I look at this, I'm like, okay, well, here I am. V1 though is equal to 0 volts. I already solved that. So I actually can solve immediately that VS is equal to 0.7 volts. Now, Kind of makes sense for a circuit like this where you're in series with a resistor, but you can also have other circuits where maybe you have some parallel combinations where you might need more voltage from the source to turn it on. But in this example right here, you basically just ramp this up to 0.7, it turns the diode on, and then from then on out, as you ramp it up to 0.8, 0.9, 1 volt, 2 volt, 3 volt, the diode stays at 0.7, current continues to increase, and then all the rest of the voltage is across the resistor. Okay, that is it. That is the constant voltage drop model for a diode, and that introduces abstraction, which is how we solve circuits that have devices in it that are nonlinear or maybe more complex than we really care about. All right, that is it, and see ya.